Let's get started. Those of you that were here last year will remember Vassili. So he's a climatologist, or yeah, he's he works for the Climate Science Center at CSIRO in Australia, in ocean and atmospherics. From the things I said in the morning about being interdisciplinary and talking across disciplines, we met Vassili last year, and we've had various conversations. We haven't quite nailed a project to work on together, but we've been talking about it. Vassili, comes with a strong track record in climate science. But I was looking actually at your background. You also did a degree in finance, right? That's correct.
Yeah, that was my undergrad degree. Yeah, mechanical engineering and finance. That's right.
Yeah. So he's got a finance degree. But really, he's gone down the sort of climate science perspective, and he's going to talk to us today about how climate models affect financial markets and also the health sector. And actually, that's one of the issues that's perhaps underappreciated actually on climate change, is it's going to have severe health implications as well. And if it has severe health implications, by definition, it's also going to have some financial implications. Okay, over to you. You've got 25 minutes, and then we'll leave 5 minutes for questions and answers.
Okay, sounds good. So you can all see my screen okay?
Yes.
See me? Yep, cool. All right, thanks, Ivan. Yeah, so the title of the talk today is the influence of climate variability on financial markets and the health sector. So given the audience, I thought I'd take a bit more of a pedagogical approach, spend quite a bit of time explaining what climate models are, the various types of data that we generate from them, what they should and should not be used for, and then give some concrete examples at the very end with regards to the finance sector and also the healthcare sector in Australia. So what is a climate model? The Earth system is very complex and multidisciplinary. Essentially, solar radiation comes in from the sun at the top of the atmosphere, and this radiation is scattered, absorbed, and reflected throughout the atmosphere and the ocean in various realms. Some of this heat is retained due to the greenhouse effect, and this greenhouse effect can be enhanced due to anthropogenic carbon emissions. So there are various disciplines that are required to come up with these climate models: fluid dynamics, chemistry, biology, atmospheric sciences, oceanography, land use, sea ice. So there is no one person that understands the entire thing. So we're all just kind of do our bit to standing on the shoulders of giants, essentially, just do everything a little bit better than was done before. So mathematically, we're fortunate in that we have systems of partial differential equations that for all intents and purposes are the truth. So we have conservation of mass, conservation of momentum, conservation of energy, and scalar transport. So in the ocean, scalar transport would be salinity or salt, the various biogeochemical constituents, so phytoplankton, zooplankton. But scalars in the atmosphere might be dust, smoke, humidity. And all of these realms, the atmosphere, ocean, sea ice, land, they're all coupled and interact at the interfaces in an appropriate way. So it's great that we have this mathematical representation. However, we can't solve these equations analytically. So we need to do it numerically. And so for those of you that have heard the term of general circulation model, this is kind of what we're referring to. This is the numerical simulation of the climate. So the way that we do that, we discretize, or we subdivide the atmosphere and the ocean into these latitudinal and longitudinal boxes with various divisions in altitude as well. So this gray sphere is representative of the atmosphere, the blue is the ocean, the green is the land. So for a climate model, typical resolution of these boxes might be 100 kilometers by 100 kilometers in the horizontal plane, in the latitudinal and longitudinal plane. And it can be much higher resolution for weather simulations in a local area and over a shorter period of time. Oh, sorry. So another key point I wanted to kind of get across is that the Earth system is a truly multi-scale system. And what I mean by that, we have important time scales ranging from seconds to centuries. and also spatial scales ranging from millimeters all the way up to waves, the entire size of the entire planet. So in the climate sciences and atmospheric sciences in particular, we've observed a whole bunch of different physical phenomena that we've given names to. In reality, this is a spectrum, but humans, we like to label things. So this is by no means an exclusive list. It's just a subset of the things that we've observed in the atmosphere. So at the small and fast end, we have atmospheric turbulence through to tornadoes, thunderstorms, cloud clusters, tropical cyclones, planetary waves, and the Madden-Julian oscillation. The key point here really is that small things are fast, and as they get larger, they become slower. That's really universal across the whole climate system. And so likewise, we have similar structures in the ocean, oceanic turbulence, internal waves, internal tides, eddies and fronts, Rossby waves, again, by no means an exclusive list. Then interactions between the ocean biology and the ocean dynamics, and then additionally coupled modes. So the seasonal cycle, spring, summer, autumn, winter, how it affects all realms, the El Nino, La Nina cycle, which we'll be concentrating on a fair bit today, and then climate change. One other important point to note is that the type of simulation you run is really dictated to the forecast window you're interested in, or the time scale you're interested in. So at one end of the spectrum, we've got climate projections. So those of you that might be familiar with the term CMIP, Coupled Model Intercomparison Project, this is really the workhorse. This is a global initiative where many institutes around the world run a predefined set of climate simulations with prescribed economic scenarios. And these scenarios essentially define how much energy is consumed globally, and then hence how much emissions are generated. The ones with larger emissions produce a warmer world. The ones with lesser emissions produce a relatively cooler world. So that's really kind of one of the main data sets that the community has generated and kind of mined, if you like. In this, you would consider this as a boundary value problem. It's all about the boundary conditions. So it's all about how much CO2 we're putting into the atmosphere year on year for the next 100 years. So the initial conditions, or the starting point, the details of the atmosphere and ocean on day one of your simulation are largely irrelevant. And the typical resolution for these climate models, as I mentioned before, is around 100 kilometers squared in the horizontal. So that's what this vertical black dotted line represents. So everything to the right of that black dotted line, all of this phenomena you can see in the climate model, you can see on the grid, but everything to the left of it doesn't exist. So, but importantly, the influence of all of these unresolved processes onto the large scales needs to be modeled or parameterized in some way. If it's not done correctly, then this can lead to additional biases and distortion of the important resolved scales. At the other end, we have weather prediction and seasonal prediction. This is really all about your initial conditions. The skill in a weather forecast is all about how well you can know the weather right now. Might sound a bit odd, but we actually don't know what the weather is right now because we don't have a sensor everywhere. So there's uncertainty where you're starting from. And as the forecast progresses, that uncertainty grows. So these regimes are all about how well you can know today. And then there's this awkward regime in the middle called decadal prediction, which is what I've spent the last few years working on in particular. In this regime, both initial conditions and boundary conditions are important. So if you're interested in forecasting the next sequence of El Nino and La Nina events, it's very important to make sure you're starting at the right phase of the El Nino La Nina cycle. But likewise, if you're forecasting over a period of 10 years, over that time scale, the boundary conditions or the land use changes and the level of CO2 that the atmosphere is subjected to year on year can also become important. And to kind of put this into context of the scales of where we live, I've labeled this top axis by the scales of continents, countries, cities and villages, and dwellings. And I think this is kind of important because it illustrates the difficulty in being able to assess the physical risk of climate, because all of the climate models don't resolve scales at the scale of the individual dwelling or the individual house or asset. There are other data sets that can be called downscaling, either statistical or dynamical downscaling, that can get you into that higher resolution regime. But climate models as standard only resolve these large scale processes, not at the fine scale required, potentially required to assess these risks. And so there's actually many systems are multi-scale. The climate system is not special in that regard. So on this other secondary axis here, I've labeled the decision-making timescales, if you like, nominal decision-making timescales of certain financial actors. So I have ultra high frequency traders, hedge funds, day traders, super funds, sovereign wealth funds. We might argue exactly in where these things line up, but I think it's a reasonable first approximation. So the applications that I'm going to talk about today are concentrated on the influence of continental scale, multi-year impacts associated with the El Nino, La Nina oscillation that perhaps financial actors such as super funds or sovereign wealth funds might be interested in. And likewise in the health application, medical resource planning, hospital planning, those types of decision makers might be interested in this timescale. Yeah, and one more kind of subtle point to note, I think, again, for the audience, it might be appropriate to kind of outline this point. When you're looking to determine relationships between human systems and the climate, historical climate reanalysis is really the appropriate types of data sets you should be using. It's because these data sets are continually nudged or pushed or corrected toward the observations of the day or of the month, depending on how often it's done. CMIT models do not do this. So CMIT models, they're not initialized in any particular way. They're designed so that we can understand the response of the climate to various different economic scenarios into the future. They're not necessarily the appropriate data sets to learn historical relationships from. Climate reanalyses are the more appropriate ones in that regard. I'm not expecting you to all absorb this, but just to illustrate the landscape of climate reanalyses, if you like, there's a whole bunch of different climate reanalyses as well. Some are ocean only, that's what these blue dots are. Some are atmosphere only, these red dots are, and all of these dots line up with the appropriate grid resolution, if you like. So all the different grid resolutions. Some are coupled atmosphere and ocean. Some are coupled atmosphere, ocean, and biogeochemistry. This is a data set that we've recently developed at CSIRO. Another distinguishing feature is how many ensemble members they have. So what I mean by that is on a given day, how many possible realizations of the Earth have they generated? So these ones down the bottom here, they only have one. This reanalysis has 10. Our climate reanalysis has 96. So in that way, it's objectively the best estimate of climate uncertainty and variability available at the moment. So this data set starts in 1960, finishes in present day. It's because the observations have noise and they're partial and they're heterogeneous in time. So we don't know exactly what the climate was back in 1970, 1980, but we have this data set anyway provides a PDF of its mean and its standard deviation and whatever other statistical properties you like to calculate. So that's a bit of an aside. Getting back to the main topic of the talk, what's the appropriate framework to assess climate risk? Thus far, I've really just focused on the hazard itself. So the properties of the climate hazard, properties of the climate system, how you can forecast it and generate the data. But there are two other essential elements for determining climate risk. Those are exposure and a vulnerability. So you can imagine perhaps in the future we have a propensity for less tropical cyclones, but they're going to be more severe. If this is occurring in a region where nobody lives and there are no assets, by those two measures anyway, there is no exposure. So even though there might be an increased propensity for stronger hazards, the risk is zero because there's nothing there to damage. I mean, we could talk about influence to biodiversity and other elements of risk, if you like, but if we just stick mainly to assets and population centers for the moment, we could say that that would have zero risk. But On the flip side, if you can imagine in a highly densely populated area with old housing stock that's not necessarily resilient to high winds, for example, then a small change in propensity for extreme winds could have a drastic increase to risk if the exposure is high and all of the exposed assets are vulnerable to that class of hazard. So I kind of like the framework that this has been placed in. So this is an image from the IPCC. A further classification of climate risk is that of being either chronic or acute. So chronic risks are these pervasive, all-encompassing impacts across the economy. So how wet bulb temperatures influence labor productivity, for example. Acute risks are the ones that maybe most people would associate with climate risk, and that are associated with extreme events. So more high wind events, more floods, more fire, more tropical cyclones, or more intense versions of them, maybe they become less frequent. Within this framework, the two examples that I'm going to talk about today are that of how chronic climate risk associated with the hazard of El Nino and La Nina influence both financial markets and also the healthcare sector in Australia. So before I get onto that, though, I thought I might just explain to you what the El Nino Southern Oscillation or the El Nino La Nina cycle actually is, for those who might not be familiar. So whilst climate change is most definitely an important and significant challenge, for multi-year predictability, ENSO is really key. It's the dominant multi-year mode of climate variability. It has a period of anywhere between 3 and 7 years. Strong El Nino or La Nina events can last for 1 or 2 months, but to go from one El Nino to a La Nina and back again would take up to 7 years. And it's characterized by the anomalous temperature averaged within this dotted box. I mean, there's a whole bunch of different time series that you can use to quantify the ENSO cycle. Many of them are just drawing this box in a different area of the Pacific. But for this particular one, this is called the Nino 4 index. And this is what the time series of the Nino 4 index looks like from 2002 to 2018. So if this time series is positive, they're El Nino conditions. If it's negative, they're La Nina conditions. The larger the magnitude of the time series, the stronger the event. So here in 2008, this is a strong La Nina period. 2010, it's a strong El Nino period. So if we take this time series and we average together all of the moderate to large La Nina events and average the surface temperature, this is kind of what an average or a canonical La Nina might look like. So we have anomalously cool surface temperatures in the Eastern Pacific Ocean, and that means different things depending on where you are in the world. So in Australia, it means that Australia is also anomalously cooler than what it would be in a neutral year. And it also means that Australia is more humid. And the opposite is true for El Nino periods. So if you take all the moderate to strong El Nino periods, average them together, you get an anomalously warm Eastern Pacific, an anomalously warm Australian region, and also anomalously drier. But importantly, it doesn't have homogeneous effects all over Australia. So it's even ENSO means different things depending on where you live in the continent. So this is going to be the main phenomenon that we're going to be interested in first of all. So the two examples I have are those of improved, well, the first example is of improved commodity price forecasting using this ENSO time series. I spoke about this in some detail last year in this forum. So for agricultural commodities grown predominantly in the tropics, the example I'm illustrating here is that of coconut oil. If we generate autoregressive models with exogenous ENSO factors, those models have superior skill in forecasting the log returns of this commodity as compared to autoregressive models that do not use the exogenous ENSO factors. So as an example, here, this is the correlation coefficient of the actual log returns of coconut oil correlated with the forecast of the log returns of coconut oil. And so that forecast is made at 1 month, 2 months, 3 months, 4 months, all the way out to 24 months or 2 years. So the red line is where we build an autoregressive model of the coconut oil log returns with no exogenous factors at all. And so arguably, we've got some skill out to 3 months. This gray region is a region of correlation that's statistically indistinguishable from zero. So you want anything outside of this gray region is arguably skillful in some regard. So at the other extreme, if we had a time machine and knew exactly what this ENSO index was in the future, that would give us this blue line. So this is the correlation coefficient between the best we can possibly do in forecasting these coconut log returns with perfect ENSO information. And we get statistically significant skill all the way out to 24 months. These solid circles indicate that it's a statistically significant better model than the red line. But in reality, we don't have a time machine. We don't know what ENSO is going to be into the future, but we do have climate models. So we can use these climate models to forecast ENSO and then use those ENSO forecasts as an input into our autoregressive model of coconut oil. And that gives us this, the cyan line. So again, skillful out to 2 years and statistically significantly better than the no ENSO model up to 14 months. Bearing in mind, that test takes into account that there are more coefficients in the autoregressive model. But what if you don't have a climate model? You can still do pretty well if you're just doing an autoregressive forecast of ENSO itself. And that's this green line. So not quite as good as the climate model itself, but all of them demonstrate that incorporating climate information into your forecast provides you with additional skill. And to kind of relate things back to the physical model, if we correlate the coconut oil log returns with surface temperature of the earth, then we get a pattern that looks qualitatively like the canonical ENSO. So I might just go back to the previous slide so you can recall. So this here is what an El Nino period looks like. Warm Eastern Pacific, warm Australia. And so we can see these similar features in this correlation map. So again, this is just another indicator that during El Nino periods, the log returns of the coconut oil commodity are increased. And these stars are predominant locations of production, this commodity. So last example, this is how the Australian intensive care unit admissions are influenced by the same physical phenomena. So for stays in the ICU that are greater than 3 days, so in this diagram from 3 days onwards, relative to the previous year, the Nino index correlated to this growth rate is negative. So what that means, and it's statistically significantly so, to like a less than 0.01 p-value. So what this means is that La Nina events are associated with longer lengths of stay. And for stays that are less than 3 days, they're positively correlated with a Nino index. And a positive value of that index means it's an El Nino event. So shorter lengths of stay associated with El Nino, longer lengths of stay associated with La Nina. And also, regardless of length of stay, mortalities are higher across the board during La Nina. And bearing in mind, La Nina is a more humid period in Australia. And this is also consistent with there being more mortalities and more admissions during winter in Australia as well. And there's also a growing body of literature in the medical journals concerning the influence of humidity on mortality, lung function, and a whole bunch of other conditions. And the intention is to use this relationship to assist in hospital resource planning. So if we have a forecast for the following year, if there's going to be a strong La Nina occurring, then that's some information that we can feed to the hospitals, and maybe they can better staff the ICU or prepare in some other appropriate way. So just some concluding remarks. The climate and human systems are both complex and multi-scale in their own right. However, there are informative relationships between the climate hazard and exposed assets for certain spatiotemporal scales. For example, on multi-year timescales, the El Nino Southern Oscillation influences agricultural commodity prices, and the Australian Intensive Care Unit admissions. These relationships learnt between the climate variability and human systems, i.e. the vulnerability, can inform how these human systems might respond under various future climate change scenarios. One other point to make here, I think, is that learning these relationships directly from climate change signals is challenging, due in part to the sampling of these very long timescales. If I've got one more minute, Ivan, I might just mention the Climate Resilience Enterprise. It's an initiative.
Yes, go ahead. Keen
yeah.
to talk about that.
Yeah, so we can talk about this more on the panel discussion as well, if you like. But this new initiative, we're trying to better enable industry to assess, mitigate, and adapt to their own climate risks. Some of the things that we're doing are developing a climate marketplace in conjunction with Microsoft to host a set of curated data sets, forecasts, projections, and reanalyses, and some guidance in how to use these. We're developing some analytical methods and example workflows to enable the assessment of physical, chronic, and acute climate risk. In the transition risk side, we're also undertaking integrated assessment modeling for a broader range of economic scenarios, rather than only those presented in the Network for Gridding the Financial System or the CMF6 exercise. This is to better assess the breadth of transition risk. And these models are tailored to an Australian context and our trading partners. We're also looking for collaborators and partners to further develop this ecosystem, keen to further engage with our New Zealand partners. So if anyone's interested, please feel free to reach out. That's it. Thank you.
Wonderful, Vassili. And I think it's really, your scale graph is, I think, really important, right?
Yeah.
Contextualize a lot of the issues that what we're trying to do. And I think one of the things I want to talk about in the panel is, there are consultancies that are using climate models to make, projections of risk in 10 years time. And you look at your chart and yeah, that's well, even a year's time. It's not a great idea, right? It's at the border at best, right?
Yeah, I think it just requires a bit of a nuanced thinking. So I understand we want to assess, say, the prevalence of extreme wind events in a warmer world, for argument's sake. And if these wind events are a very small scale, the climate models themselves don't resolve these processes. So there's a few ways forward. You can statistically downscale or dynamically downscale these data sets. Statistical downscaling is computationally cheaper, but it's arguably less informative than dynamically downscaling. So dynamically downscaling essentially means running another model in a local area with finer resolution. These are really computationally expensive, and I can't imagine that being systematically done for every climate scenario and every model. But yeah, so I guess that's kind of what's needed. Some higher resolution climate data that's appropriately generated for the future scenarios. But I don't think we're there quite yet.
I think I had a question, but I don't know if there's any questions from the audience, or we can all save them towards the panel. And you've got, so I should have really introduced that. Really, this section is all about modeling climate risks. And so we've got two keynotes and then a panel involving the keynotes and two practitioners. So I think, so one question I had is in terms of how climate change affects El Nino, La Nina. Do you have any?
Yeah. So that's a really interesting question. And the issue is sampling. So satellites only went up in the 1970s. So we've only really got a reasonable estimate of the climate from 1970s onwards, I would say. And rightly, the quality of the observations and density of the observations has been increasing with time. So our certainty in the climate is better now as it was in the past. And our climate reanalysis kind of captures that. You can see the standard deviation of all of our Earths getting smaller and smaller with time. But to kind of get to your question more directly. Since let's kind of be generous and say El Nino cycle is on the short end, so 3-year period, from 90 over, say, the past 60 years, we've seen maybe 20 of them, less, more like 15 probably, and on top of that, we're trying to see a relationship between the periodicity and strength of them with a slowly growing underlying climate change signal. Like statistically, it's an incredibly difficult task. So you can assess them in climate models. So you can see into the future, what are each of the different CMIT models say in terms of how frequent and how strong the El Nino cycle is. But I mean, there are issues with how well that process is represented in each of the different models. So it gets down to this parameterization problem, this black dashed line. So if all of these small scale interactions are not represented properly, then that can distort what El Nino and La Nina do, both now and into the future. So most of these models are tuned to best represent what we've seen, which is a reasonable approach, but that's not to say that these parameterizations should not be modified in a warmer world. So there's some, so it's a difficult question. A lot of smart people working on it, but I don't think we can say anything definitive at this point.
There's a lot of uncertainty in terms of how the actual effect will happen under.
Yeah.
Cool. We'll move on, and we'll have you back on the panel if you can unshare your screen.
Sure.
So we'll move over to Jesse, and we'll continue this discussion.